are nodding. So first of all, I would like I would like to thank the organizers for giving me the opportunity to speak here. And I must say I was thinking a lot whether I should speak about finite forcibility, but I had a feeling I spoke on that topic a lot. So many of you have heard me talk about it. And I decided to speak about quasi-randomness and the interaction of quasi-randomness with combinatorial limits. So there will be graph limits, but there will be also limits of our combinatorial objects. And I should say that I will be focusing mostly on the results when the theory of graph limits actually had an impact on the proof. So most of the proofs, even if I will not present them, were like coming from the theory of combinatorial limits. And I will not be mentioning some recent work on how to define quasi-randomness in various settings due to Corigliani and Rasborov, and I will also not mention quasi-randomness results very many, which are not like so much related to the combinatorial limits which existed before, in particular to the hypergraph quasi-randomness. There's a lot of work because it can be defined like the various various degrees of quasi-randomness, but I want to mostly focus on the interaction of combinatorial limits and quasi-randomness. But I will break my promise already on the first slide because I want to start with an introduction. So I will start with some classical results which actually existed well before quasi-randomness, before combinatorial limits, and I want to talk about the results from the from the early 80s about quasi-random graphs due to Chung, Graham, Wilson, Rödl, and Thomason. So what does it? So when we speak about quasi-randomness, we want to say that a particle combinatorial object looks like a random one, which usually is not a question which is a question about a single object, because let's say we take the Erdős-Rényi random graph, which is the most classical model for random graphs. So any graph can be a result of this process. But we rather wish to look at a sequence, and we want to say that this sequence has the properties that a sequence of graphs which would be generated by the Erdős-Rényi random graph process would have asymptotically almost sure. So when I want to speak about quasi-random graph, I actually don't mean a single graph, but I rather mean a sequence of graphs with increasing orders. And the same will be true for our combinatorial objects that we will see during this talk. And as I mentioned, the theory of quasi-random graphs goes to the 80s. And so when I want to say that a graph is quasi-random, so it will be a property of a sequence. And I want to say that the density of any graph in the sequence converges to its expected density in the Erdős-Rényi random graph. And during this talk, I will have like two different densities. So one is the induced density. So let's say H has k vertices. I take a randomly chosen uniformly k vertices of G, and I'm looking whether those k vertices induce G as a subgraph. And the other will be the homomorphic density. I take a random mapping from the vertices of H to G, and I want to see what is the probability that this mapping is a homomorphism. And it's not hard to see that actually, if I require that the induced density of every graph goes to its expected density, then of course the homomorphic density goes as well. As an easy application of principle of inclusion and exclusion. And this is the definition of quasi-random, a sequence of graphs which is quasi-random. And it turned out that this notion is particularly robust because it's equivalent to many different properties. Most famously, that actually instead of checking this property for all graphs, it's enough to check it for two graphs. So it's enough to check that the density of edges goes to P, because this would be what would be the expected edge density, and the homomorphic density of C4s goes to P to the 4th. So if I take the Erdős-Rényi random graph, so I would require, if I take a random mapping, that the cyclically ordered vertices will map to C4, and this will happen with probability P or P to the 4th. So I kind of prepared here some pictures. So instead of checking all graphs, one can check an edge and C4, but this is actually equivalent to many other properties. So for example, if I take an n-vertex subset where n is not the total number of vertices, but is linear in the number of vertices, then the number of edges on that subset will be roughly the expected edge density. So I can take a linear size subset of vertices and look what is its edge density. And if the edge density on every linear size subset of vertices is what one would expect it to be when all the three previous properties also hold, and vice versa. Instead of looking on the number of edges inside, I can take two random, let's say, disjoint subsets, again, linear size, look at the number of edges between, and again, this is equivalent to all the previous properties. And I can also look at the spectral properties, so I can look what is the adjacency matrix. Let's say now n is the number of vertices of my graph. So I expect the largest eigenvalue to be p times n, because I expect that my graph will be roughly p times n regular. Of course, it won't be exactly regular, but close to. And I expect all the other eigenvalues to be sublinear. And there are many other, but I just wanted to mention these five. And this kind of that shows that this is a very, very robust notion, because this one definition is actually equivalent to many others. And now let me, because this is a workshop on combinatorial limits, now let me cast some of these results in terms of combinatorial limits. And to do that, let me actually introduce the notion of graph limits and their analytic representation, which is called a graphon. Even if I assume that most of you have seen it, but let me still quickly go through this notion. So first of all, I want to say that a sequence of graphs is convergent if the densities of subgraphs converges. I have chosen here the homomorphic density, but of course, if the homomorphic density of every subgraph converges, again, an easy application of principle of inclusion and exclusion is that the induced densities also do converge. And in this definition, quasi-random means that the sequence is a sequence of graphs is quasi-random if it's convergent, and the limit of every density is the expected density in the Erdős-Rényi random graph. And every convergent sequence, that's a result by Lovász and Szegedi, can be represented by a graphon, which is a symmetric measurable function from the unit square to a unit interval. And the kind of the naive view of graphon can be as a continuous version of adjacency matrices, but I should say this is a huge oversimplification. But let me still sell it as a continuous version of an adjacency matrix. And I prepare here an illustration. So if I take a sequence of graphs which are complete bipartite graphs with the number of vertices in the ratio 1 to 2, then this would be the adjacency matrices. And when the limit will be this graphon, so the origin is in the top left corner to make the analogy with the adjacency matrices, these two parts will be 0 and these two parts will be 1 to represent the edges between the parts. And it's possible to define the homomorphic density of a graph in a graphon. So if one thinks like how would one compute this for an adjacency matrix, it will be like a sum over all vertices and then 0 ones, and one replaces the sum with an integer and gets a definition for a graphon, and it actually works very well. And I prepare here pictures of some other graphons. So this one is the complete bipartite graph with parts of equal sizes. This one is actually the graphon which is constantly equal to p, and this is the graphon that actually represents the sequence of quasi-random graphs, because we expect no structure, we just expect the edges to be uniformly distributed, which is exactly one of the conditions that I have shown earlier. And this graphon is the graphon where I have a clique on half vertices, quarter, 1/8, and so on. So as the n would be growing, I will see cliques, and one of them will be on half of the vertices, one on a quarter, and so on. So let me now cast the previous result in the language of graph limits. So a sequence of graphs is quasi-random if and only if the limit is either half or p, depends like how we view it. And when this is what is the result on the C4 and K2 to cast in the language of graph limits. So if I have a graph on W, the homomorphic density of K2 is p, the homomorphic density of C4 is p to the 4, when that graphon is equal to p almost everywhere. And what I want to do during this talk, so this result existed before the theory of combinatorial limits, I want to present various results of this kind, but actually the theory of combinatorial limits provided suitable tools for proving. And I just want to mention that this actually implies also this, but maybe let me, in the interest of time, since we already late, and maybe let me just skip commenting on this. So I want to mention some various results, but let me stay a little bit longer with graphons. and I want to mention particularly step graphons. So a step graphon is a graphon where vertices can be, or the interval can be partitioned into subsets, into finitely many subsets, and the value of that graphon, for if I fix one part and another part on that part, is constant. So this is also called the stochastic block model. And one of the early results in the theory of graph limit is due to Lovász and Schoch, and they showed that if that the case step graphon is actually characterized by densities of subgraphs with these many vertices. So we had like in the case of one step, we knew that we checked the density of K2 and C4 when this captures it forces the graphon to be constant. And when they generalize this, that instead of having one part, if one have K parts, then this many vertices will suffice. And when this actually was improved by Lovász, that actually a polynomial number of vertices is enough. And then of course the question comes whether this is optimal. And I want to sell here a recent result that I have with Andrzej Grzesik and Oleg Pighurko, which actually shows that this polynomial can be brought down to quadratic. Unfortunately, we were trying to prove a lower bound, and besides the rather easy linear lower bound, we don't know whether this is optimal. So perhaps like this can be brought down to linear, but maybe quadratic is the right step. And of course, like there's actually better results in case one assumes that if one takes the row integral, kind of the degree, if these differ for parts, and Spencer actually showed that linear is enough in case the degrees of parts are different, and our methods actually improve this from 8K to 2K plus 1. I wanted to make this slight detour just to show that, first of all, mention some very recent results, like just 2 weeks old, and also like to mention that one can not only consider like quasi-randomness in the very classical sense, but also consider more general notions like this step graphons. So let me now switch to other type of combinatorial object, namely a tournament. So a tournament is just an orientation of a complete graph. So I put here some pictures. These two are actually transitive tournaments, which means that one can order vertices in a way that all the edges go from a smaller vertex to a larger vertex. So this is a transitive tournament on 5 vertices. This is a transitive tournament on 6 vertices. And again, there exists an analytic representation, which is called a tournamenton. It's a measurable function from the unit square to unit interval, but instead of the symmetry condition, one has this complementary sum condition, which somehow represents that one has an edge either in one or the other direction, or sometimes the density of edges is like basically it kind of captures what the regularity partition would give. So in particular, this tournamenton is a representation of a sequence of transitive tournamentons. This one corresponds to the random one. We see no structure. The edges go in both ways. And this is just an example of a little bit more general tournamenton that I wanted to include. So now, of course, the question comes, are there any tournaments T such that if the density of a tournament, let's say homomorphic density, is what it would be in what is the expected density in a random tournament, which is just a tournament obtained by randomly oriented edges of complete graph. So the question is, are there any tournaments such that if in the tournamenton or in the sequence of tournaments, if one wishes to look at the limit, the density is what one would expect it to be when the tournamenton must be 1/2. And actually, there are results already from the 80s that every transitive tournament with at least K4 vertices has the property. So this can be found in the Lovász's book Combinatorial Exercises, and then an alternative proof using the Fleck algebra method was given by Parent and Razborov as one of the early or examples of the early examples of application of the Fleck algebra method. So the question is, are there any further tournaments in addition to these transitive tournaments? And the answer is yes. So where is this 5-vertex tournament, so which I have just shown here. So we have here 2 cyclic triangles sharing a vertex and all edges going from left to right here. So this was proven by Coregliano, Parente, and Sato in 2019. And now once we have an example, one would be hoping that there would be infinitely many. So this is actually not the case. Bucic, Long, Shapira, and Sudakov showed that there is no 7-vertex tournament that would be forcing quasi-randomness. And we actually we're studying also more general settings of quasi-randomness in tournaments, but this is a particular corollary of one of the results. And then with Robert Hancock, Aranka, Cabela, Taisa Martins, Roberto Parente, Fiona Skerman, and Honza Volec, who's in the audience, we actually showed that there is no additional tournament. So somehow, surprisingly, transitive tournament and this special one are the only tournaments that capture quasi-randomness. Of course, now one can go with pairs of tournaments or triples, but if one wants just a single one, then these are all. And again, these results were based on the analytic representations of tournaments.
This is a bit counterintuitive compared to Chung Wilson right there. I mean, if you have C4, density of C4 or C6 or C8, any C2T would work, but here.
So the question is that it's slightly counterintuitive. I would actually, I mean, it depends, because so there's actually an analog of this C4, and I will actually mention it in maybe not explicitly, but I will get to that on 2 slides later. But I think maybe the counterintuitiveness might come when one has just 1 instead of 2. But on the other hand, there's nothing like edge density, right? Because the edge density is simply half. So somehow replacing 2 with 1 is not so counterintuitive. But neither of these, I mean, okay, this. Let me comment on it when I get. I mean, I didn't prepare it, but I want to comment it when I have the proper setup for it. Yeah, thanks for the question. So now I want to do a detour, which I prepared because I found it. First of all, it's another application of the theory of combinatorial limits, but also it will provide some other characterizations of quasi-randomness of tournaments. And but I want to start from a different problem, which is the question about the density of cycles in tournaments. So if I'm looking at what is the minimum and maximum density, and I'm considering a cyclically oriented cycle, when the minimum is easy, it's 0, because in the transitive tournament I will not find a cycle. And the question is, what about the maximum? And clearly I can get at least as how many cycles of length k I can find in a tournament. And let's say I'm looking in the asymptotic version, so I'm looking at the maximum density, and I want to compare it with the random tournament, because if I take a random tournament, I can compute what is the expected density of cycles of length k. So this is clearly something that I can get, and the question is how better I can get. And this is again a question which was studied for small k well before combinatorial limits. I think actually in the 40s it was showed that in case of 3 cycles, if I take a cyclically oriented triangle, then one cannot do any better. Somewhat surprisingly, for 4 cycles, one can do 4/3, and I will show a construction in a minute. And then somewhat recently, Komarov and Mackey showed that for C5, one can again not do any better than the random. So now it seems like there might be some pattern, but the question is, what is the pattern? And there was a conjecture due to Barkley and Day. I don't think they made it independently because they were students at the same university. And they conjectured that CK is 1 if and only if k is not divisible by 4. So the pattern would be 1, then something larger, 1, 1, 1, something larger, and so on. And they also conjectured what the value should be when k is divisible by 4. So they didn't have this formula. They provided a construction. But when one look what is this construction doing in the limit and looks at the limit tournamenton, when you're just using its spectral properties, this would be the formula that comes out. And using the And actually using the spectral properties of tournament limits, Tournamenton, we resolve this problem. But before I get to that, I should show you the construction. So the construction of this for this 4/3 and also for any k divisible by 4 is the following. So one takes the vertices ordered on a cycle, like, and when from each vertex one draws an edge to the forward half arc of the cycle, and the edges from the backward comes to the vertex, and when one rotates. So basically vertices are ordered cyclically, and to the coming half of the vertices one has an edge going to and an incoming edge from the other, so kind of rotates it around. And if one looks at the limit Tournamenton, then one can actually look at its spectral properties, link it to the number of cycles, and this will be the formula one gets. And somewhat surprisingly, if k is not divisible for 4, then actually this one does not give anything better. Sometimes actually gives less than 1, like if in particular if k is even and formal. I already said that we managed to prove this first part of the conjecture. So with Andrej Grešik, Laszlo Miklos-Lovász, and Honza Voles, we showed that actually the conjecture is true. So one can do better if and only if k is not divisible by 4. And when we actually showed that we didn't prove the conjecture, but we showed that at least the leading term in this sum is what one would expect. So we showed that the ck is if k is divisible by 4, it's between 2 times 2/π2k, which is the leading term in this sum, and it's at most 2π plus little over 1 to k. And we also verified the conjecture for the next open case, which is C8, which gives 3, which is this fraction, which is the value of this sum. So it provides an evidence that this is most likely the answer, but we were not able to prove it for larger values of k. But why I talk about it, but somewhat surprisingly, one of the products of our results is that if k is 2 modulo 4, when we can achieve the density of cycles as in the random tournament, if and only if the spectrum is actually half 0, 0, 0. So actually the cyclic orientations of cycles of length 6 force the quasi-randomness. And likewise, the cyclic orientations of cycles of length 10, the cyclic orientation of cycle of length 14, and so on, because it forces the spectrum and therefore it forces the tournament. And I don't know whether maybe it's now a good time to make a detour. Let me try to use a marker, which hopefully is not a permanent marker. And when we were looking at different orientations, and basically the argument is the same as if one wants to prove the Chung, Graham, and Wilson using analytic methods, when the C4 in the case of tournaments would be replaced by this orientation of a cycle. So this would be, and when this orientation would be quasi-random-forcing, and when one thinks about it a little bit further, let me try to. When these two vertices are twins, and these two vertices are twins, so it doesn't matter if I find this orientation in my tournament, when how I orient the edge between them, and this is actually a transitive tournament on 4 vertices. So this orientation of C4, which actually would correspond exactly to Chung, Graham, and Wilson, and the proof is almost the same if one would be proving it in the language of graphons, would be the analog, and then the order 4 is the corresponding case.
So when you in graphons there appears something which we physicists would call reflection positivity, but there is sort of some Hilbert space where you can sort of bounce things by C4, but you use some positivity of some scalar product. So how does that work here?
So I mean, I'm not quite.
What I'm talking about.
I don't know what you're talking about, and I will be very happy to discuss it during the coffee break. But actually, the proof is again like just by some cautious ones. So I think that,
okay, fine.
So I would expect the answer is
it's a cautious ones, yes.
It's the same. So So now we know, like by this result, that the cyclic orientation of C4 is not quasi-random forcing. However, that orientation of C4 is. So the question is whether it would be possible to actually say which orientations are quasi-random forcing. And we thought it would be rather an easy exercise when basically one inspects spectra, but it turns out that it was quite challenging. So we didn't manage to do a full classification. We have a full classification of length up to 12. So it's a joint work again with Andrzej Grzesik, Daniel Lenkovic, who's a student of mine, and Bartek Kilak, who's a student of Andrzej. And first of all, we actually showed that no orientation of an odd cycle is quasi-random forcing. We have a full characterization of orientation up to length 12. And I prepared here just that you can appreciate that we don't have even a working conjecture what might be the orientation. So we have some general theorems which covers most of the cases, but in some cases we needed some ad hoc arguments. Up to length 10, it's actually true that if the density, if one compares the density in the transitive tournament and this special tournament which was showing 4/3, if they on the same side from the random tournament, then it's quasi-random forcing, but actually it breaks out for the length 12, and we currently don't have any generalization. And all these results were obtained by the analysis of the spectra of tournamental. So it's again like an application of the theory of combinatorial limits. So I think I started like 55 maybe.
Yeah, so you have still like more than 10.
Yeah, I would assume I have still 15 minutes. Like, can I go with 20? Okay. So let me now switch a page. So there are two more combinatorial objects I want to talk about. I want to talk about permutations, and I want to talk about Latin squares. And if time does not permit, I will skip the Latin squares, but I have just 2 slides on them, so hopefully I will manage. So for a permutation, I want to define again like what is a quasi-random permutation. For that, I need a notion of subpermutation, which in those working with permutations would actually call a pattern. But because I am trained to be a graph theorist, I will be using subpermutation, and I do apologize to those who are more from the permutation world. And rather than a formal definition, I prepare a definition by a picture. So this is a large permutation, and I want to look what is a subpermutation induced by those points which are underlined. So I just take them. The smallest one becomes 1, the second smallest 2, the largest is 3. Here's another example, and I should emphasize here that because I'm a combinatorialist, I'm not looking at any algebraic structure, so it's not a mapping for me. I'm not looking at any signs. I'm just looking at the permutation as 2 linear orders, one kind of sorting the elements from left to right, the other one just saying which element is 1, which element is 2, which element is 3, and so on. And a natural definition, if I have a sequence of permutations, then I will say it's quasi-random if the density of every pattern or every subpermutation tends to 1/k factorial, which is the number of permutations of order k. And if I take a sequence of randomly chosen permutations of increasing order, it's quasi-random with probability 1. And when Graham, and the source is not quite clear, but at some point in the 90s asked whether actually the same phenomena that I have been describing for graphs exist for permutations. So namely whether there exists K0 such that if the density of every permutation of the K0 goes to 1/k factorial, which also implies that the density of all smaller orders goes to 1 the order factorial, then whether this is describing the quasi-randomness. And so before I answer that question, so let me define what is a permutation limit. So if I have a convergent sequence of permutations, which means the density of every subpermutation converges, then the limit, which I will be referring to as a permuton, can be viewed as a probability measure on a unit square with something which is called unit marginus. So I prepared here a picture. So what do I mean by a unit marginal? So this is my unit square. And when I want that if I take a horizontal rectangle going from left to right, when it's a measure, it's its height. And if I take a vertical rectangle going all the way from the bottom to the top, when it's measure, it's its width. So I want kind of, if I project to the horizontal axis, I get the uniform measure. If I project to the vertical axis, I get the uniform measure as well. So I prepare here some examples. So if I take the measure with the support on this diagonal, that corresponds to a sequence of increasing permutations. This is a sequence of decreasing. These are like, let's say, if these are like two sequences which are increasing. Let's say I have here like odd points and here I have even points, and this uniform measure will correspond to the sequence of random permutation. And when I can define like a density of a small permutation in a permuton, which I will just define by taking n random points. So let's say these. I prepare here a picture, and when I sort them according to the x coordinate, and when the y coordinates determine what the points are. So this is the smallest, so becomes 1. This is the second largest, becomes 2, and so on. And when one can do a link that for if I have a convergent sequence of permutation where exists a permuton, such that the densities or these probabilities that a mu random permutation of a particle order is what one would expect is the particle permutation are actually the limit densities of both subpermutations. So in particular, the question now that Graham was asking is, does there exist K0 such that if the densities of subpermutations of order K0 are 1 over K factorial, then the measure must be uniform. And with Oleg Pigurko, we actually answered this question, and we really work in with permutation limits. And when it actually turned out that there exist results in statistics which are related to independent tests, which actually are also answering the question. So in particular, Hevding in 1948 proved a result which is actually equivalent to this statement for K0 equal 5. And Yanagimoto in 1970 improved this Hevding's result and actually essentially proved like this equivalence, of course, using the notions from statistics. And I just want to mention that K0 free is not sufficient. So let me actually present it now, like if I introduce the language of permutation limits. So let me present it using this language. So I take the measure with this support such that the mass of the measure is equally distributed along these two diagonals. And it can be, by a direct computation, it can be shown that the density of 1, 2, 3 in this permuton is 1/4. The density of 1, 2, 3 in this permuton, or well, the measure is like this is the support, and again like equally distributed is 1/8. And now I take a smooth transformation, so I kind of think of these as two thin rectangles, starts opening them, keep opening them, at some point they become almost square, and once they coincide, when is this measure. So at some point during this smooth transformation, I will have a density which is 1/6. But because this is symmetric, if the density of 1, 2, 3 is 1/6, the density of 3, 2, 1 is 1/6. The remaining 4 are symmetric to each other. The sum of the densities should be 1, so the density of each of them is 1/6. So, and this is clearly not a uniform measure. So once we have this result, then of course the question now might come: do we need all 24 permutations? And that's actually is of interest to people in working actually in big data and in statistics. And this is actually how we discovered a connection, because we noticed that one of the papers in that area actually cites our paper, and we look what they're exactly saying, and we also notice they cite these results. And let me skip this result then. So the question is, do we need all 24 permutations? And the answer is no. We can go with 8 element set, and I will present that on the next slide. But let me say that the current record is actually 6 permutations, which was proven recently by John Noel and 2 students of his, Rödl and Dukes. So they have a set of 6 permutations, but notice that here I am saying they have an 8 element set of 4-point permutations, but these permutations are not of order 4. They have mixed orders. And for the lower bound, there's a paper of Martin Kurečka, a student of mine, who actually showed, and again using like analytic methods, by studying like the perturbations of the uniform measure, that one would need at least 4 permutations. So if one wants to have a set of permutations such that if one looks at the permuton and the densities of these permutations are what they should be, when and this would imply that the measure is uniform, then that set must have at least 4 elements, and even if one allows mixing the orders. So the general bound, if one allows mixing the orders, is 4 and the answer would be between 4 and 6. If one wants to have a subset of 1/24, then the answer will be between 4 and 8. So let me show you some of these sets, and we actually, and again we were like looking at the permuton and studying like the perturbations and so on. So we were actually looking at a slightly more general question. So instead of looking at the density of every permutation in the set, we were looking at the sum of the densities, and we actually characterize all subsets of 4-point permutations that are forcing quasi-randomness in this stronger sense. So these are the 3 8-element ones. This one is the 12-element ones. Of course, if this one is forcing quasi-randomness, then the complement as well, because if the sum of the densities of these 8 permutation is 1/3, the sum of the complementary, the densities of the remaining permutation must be 2/3. So the characterization goes that a subset of 4-element permutation forces quasi-randomness in this sum forcing way if and only if it is one of these 4 sets, or it's symmetric to it. It's meaning like it's rotationally symmetric, or it's complement. It's a complement of it. And even if one would require, instead of looking at the sum, looking at the density of each of the permutations individually, no smaller set is known to force a quasi-randomness. And I think I still have like 5 minutes. So I am allowed to speak about Latin squares. So we all know what is a Latin square. So a Latin square is just a matrix in every row and every column there's a permutation of numbers from 1 to n. And one can define a subpattern density, which would be defined by saying, okay, I select some columns, some rows. So let's say I select the 2nd column and the 3rd column, 2nd and the 4th row, which means I'm picking up these 4 elements, and I just look again at their relative densities, and this gives me that this is 1, this is 2, this is 3, and this is 4. Some of them might be actually equal, in which case I get 2 equal numbers. But if I have a large randomly selected Latin square, when this happens with a small probability, it also more precisely, even more strongly, even for a fixed Latin square, this happens with a small probability that if I pick a random subset of rows and columns, I will see the same element. So I can ignore both patterns. So this is the definition of pattern density. And there's a limit theory, which is actually somewhat non-trivial for various reasons. So first of all, one needs to come up with the right notion of regularity partitions, which is actually less tricky. And then more importantly, one needs to say when one has a limit object, like arguing that actually for every limit object there is actually a sequence of Latin squares converging to it, when this is the non-trivial part, and one needs the recent powerful results on the existence of the designs due to Kivash to actually do this sampling. So the limit theory was developed by Frederick Garbe, Robert Hancock, Honza Hladký, and Mariam Sharizadeh, and they asked like whether there's a similar characterization of quasi-randomness as for other combinatorial structures. In particular, like whether one can just look at patterns of first of all finitely many patterns, or patterns of some small sizes, such that if their densities are what they should be, then this would imply the quasi-randomness. So this is the question, or a conjecture. So does there exist K and L such that the sequence of Latin square is quasi-random even only if the density of every K times L pattern, K is, let's say, the number of rows and L is the number of columns, converges to 1/KL factorial.
I don't understand the red and the black in the
Yeah,
square.
because there's a red 5, which doesn't appear on the right.
Yeah. So the question. So I repeat the question on the mic. So those who follows remotely. So the question is about how the sampling is defined, or more precisely the subpattern or patterns are defined. So what I understand was clear when one selects some colors and rows. So one selects some colors and some of the rows.
Okay.
So I have chosen here the second column and the first column, the second row and the fourth row. So now I'm looking in this case in the square, and more generally I will be looking at the rectangle. And I am looking what elements I do see where, and when I read them similarly to the patterns according to their orders. So the smallest one will be 1. The second smallest, which is this 3, will become 2. The first smallest will become 3, and the largest will become 4. And if one has it's not a Latin square, and even more generally, like if one has a sequence of Latin squares, then the densities of those that do actually repeat a number will go to 0. So the limit densities will be non-zero only for those where all these, in general, let's say I sampled k rows and L columns, all these k times L numbers are distinct. And because if I have a huge Latin square, the probability that I will hit like 2 entries which have the same value goes in the limit to 0. So the densities of the patterns that are of interest are only those where all these numbers are different. So we're very non-Latin squares actually. They're more like some kind of generalized 2-dimensional permutations. And the conjecture of Frederick, Robert, Honza, and Mariam, who developed the limit theory for Latin square, was that there's a finite characterization, that there exists K and L, such that if the density of those patterns that have the right to be non-zero is what it should be in a sequence of kind of truly random Latin squares, when the corresponding limit object will be the uniform one. I don't want to say it will be like equal everywhere to something because it's somewhat complex object. I intentionally didn't define it, but that this will capture the Quasirandom.
You need to define it not just on squares, but on rectangles.
Yes. And this is the result. So using their theory of limits of Latin square, we actually showed that it's enough to take k to be 2 and L to be 3. So if one just looks at the rectangles 2 times 3, and the density or the patterns 2 times 3, and the density of each pattern goes to 1/720, when the density of every KL pattern which does not repeat entries goes to 1/KL factorial. So this would imply that the factorial. And we also show that 2 times 3 cannot be replaced. It's 1 times L or 2 times 2. So this is the best possible. So one option might be that one decreases one of the coordinates and increases the other. That's not possible. And likewise, like going to decrease this 3 to 2. So we have examples again using we didn't construct like it. We construct the limit objects explicitly, but we didn't construct the Latin square. We just like use this sampling result that I mentioned. So, and I think I just ran out of time. So I presented various results on quasi-random combinatorial objects that was proven using the methods from the theory of combinatorial limits. And there are plenty of open problems. My favorite is clearly finding the smallest quasi-random-forcing set of permutations. And let me just thank you for your attention.
Thanks, very nice talk. So yeah, questions?
So as was pointed out by Jans and Diakonis, the results of Lovász and Szigeti actually follow from an old result of Aldous and Hoover. And in general, they have this nice view of graph limits as a question of a sampling question in statistics. So do these other notions which you mentioned, can they formulate it instead of talking about a continuous graphon, talking about some probability measure on some infinite combinatorial object? So to some extent, one would say the limit of a sequence of graphs should be an infinite graph. That's false. But actually, Aldous Hoover says the limit of a sequence of graphs is a random infinite graph. And so is there some similar notion for your Latin squares? Is the limit of Latin squares somehow an infinite random lattice square? Latin square.
So the question is about like, so I will, okay, I'm not sure I can reformulate the question to repeat. Oh, no, you had a mic, so I don't have to actually. So everybody followed. So I would be thinking, so my impression is that there's clearly a freedom in choosing these limit objects. So I would be thinking the answer is yes, just by that there are very different views on the combinatorial objects, like all these limit objects, like the graphons and these early results you mentioned. And I would think that would be the same for Latin squares. In particular, like the object that, and I mean, if I somewhat oversimplify it, it's more or less like a graph with ordered set of vertices, so and colored edges. So basically, it's actually very similar to like in some spirit to graph limits.
So let me ask you a question which.
So you could, so your infinite object for the Latin squares, you said allows you to generate a sequence of Latin squares. Is there some way to formulating when this sequence, so for sequences of random graphs, we know that if they're exchangeable, then it corresponds to a graphon. Is there a similar notion of exchangeability for these Latin squares, which would allow you to say it corresponds to a graphon?
So I would be, so the short answer is there is not, but I would be surprised if you cannot like develop it in the analogous way. So of course, like I might now be overlooking some technical detail, but I would believe that it should, I mean, it's so close to graphs that I would be surprised if there's really a problem.
I have a question that, I mean, for permutations, I mean, or permutations or Latin squares, you have a now notion of quasirandomness. So a next question would be like, do you have a notion of regularity there?
Yes.
You do.
So yes. So actually, all these limit objects, like at least if I'm coming more from the combinatorial side, they kind of, at least I view them like as a combinatorial as kind of limits of regularity partitions, and that's the case in permutations. There's like the regularity due to Cooper, which is actually different Cooper than the Cooper in the Latin square results. Tournaments, and you do the same as for graphs. And I don't think that.
And there is a notion of regularity, and you can, for example, for a sequence, I mean, for a permutation, so you have also a regularity lemma kind of thing.
Yes.
You can
So
extract subsequences and say that all are quasi-random except a small part.
Yeah. So actually the notion of regularity for permutations is conceptually simple than for graphs.
I see.
So one doesn't get the irregular pairs, for example.
Okay.
And there's also like associated removal lemmas. So there might be some tricky bits in terms like if you have a removal lemma, how you measure the distance, because there might be like various metrics on permutations, like how to say that two permutations are close to each other.
I see.
But I would believe that even in the they might be like when you kind of compare how like kind of the more like, I don't know where I would say L1 norm, but somehow like visually, or you may do like more combinatorial ones, like looking at the number of transpositions needed to transform one permutation to another. This will actually give slightly different metrics. But even for the stronger ones, there were associated removal lemmas. So the theory
much stronger than.
So in this direction, the theory has been developed.
Thanks.
So just two small questions. So first one is related to this Aldous Hoover stuff. So as was mentioned, Aldous Hoover basically says that the whole graphon stuff is related to exchangeable array of random variables. And so the quasi-random stuff of Chung, Lu et al. Basically, you can think of this as what properties about moments does this imply that you have a unique distribution for this infinite family of exchangeable random variables. And so the question is, do your results, maybe they basically give you structural properties about exchangeable family of random variables. So if you have these properties of the moments of exchangeable families of random variables, this implies you uniquely know the distribution. I mean, and the question is the other way. Are there results from the family of exchangeable arrays that imply your results? You know, like there's method of moments in statistic probability, which asks under what conditions do moments uniquely determine the distribution? And your first set of results seem to imply this sort of relationship. If you know these things about exchangeability, then this implies uniqueness of distributions.
So I would, so first of all, for most of the graphons or like other limits, like there's no like chance to like describe them by finitely many variables. So I would be thinking that the general answer would be no, but in some particular cases, the answer would be yes. And I would slightly prefer having this question offline in particular, because somehow it's getting on the boundary of my expertise. I assume the talk is recorded and I don't want to say something which I would feel very ashamed in a year.
Okay, so then the second question, this you don't have to answer, but so, you know, like going to your permutation, maybe the next slide. Yeah, so that question, you know, under what conditions do you have uniform distribution, convergence to permutation? A sort of related question is, suppose now you know not just convergence, like 1 over k factorial, but you know the rate at which something converges. So D, you know, you have a sequence of permutations, but D pi comma pi I minus 1 over k factorial, or the total variation distance is like 1 over square root n. Then do you get even more results? So for example, can you say that the distribution of permutations of length 1 over log n is also like 1 over log n factorial? And so this is something that I guess with Suman here, we have thought about this for graphons. You know, suppose in the Chung, Lu, Graham setup, suppose you know not just things converge to p squared, etc., but you also know rates of convergence. Then does that imply, for example, existence of cliques of size log n?
Yeah, so I it's a very interesting question. I don't think that this has been, at least I'm not aware it has been studied for permutations. Like I would assume that you can, like using the techniques which exist for graphs and graphons, one like can maybe, or one should be able to obtain some results, but I don't know like to what extent.
Okay, thank you.
So maybe in the interest of time, we can end here and go to the coffee break. Yeah, and then let's thank the speakers.